Good morning, everyone. So, in today's class, we are going to discuss gate problems on sampling and quantization. So, I've already discussed you the theoretical aspects of sampling as well as quantization in my previous lectures. Today, we are going to discuss some of the problems which have already been asked in the gate examination. Now, come to question number one. Uh, let xt is equal to let xt is equal to 2 cosine. Let xt is equal to 2 cosine cos 800 pi t plus cos 1400 pi t. So from here we can get fm1. Now this is equal to 400 hertz. And what about fm2? This will be equal to 700 hertz. Now this can be easily obtained by comparing this expression with cosine 2 pi ft. Now what will be the bandwidth of the signal? Bandwidth of xt. Let us call it as w. So W will be equal to, since there are only two frequency components, so bandwidth will be the maximum of the two. So bandwidth will be equal to 700 hertz. This is simply equal to 0.7 kilohertz. Rather, we should write it like this, that the frequencies present in XF are 0.4 kilohertz and 0.7 kilohertz. Right. The only spectral components present in the sample signal in the frequency range 2.5 kilohertz to 3.5 kilohertz are. Now T naught is given. Now this is the signal through which this xt is being sampled. Now this is not an ideal sampling function, but this is a rectangular pulse string. So it's given that T naught is equal to 1 millisecond. So what about the sampling rate f naught? What is the f naught? F naught is equal to 1 upon T naught, which is equal to 1 kilohertz. Right. So this f naught or 1 kilohertz is the sampling rate. Now what should be fs? Fs should be greater than or equal to 2w, but in this case this f naught, this is less than 2w, so this is the case of undersampling. Now this is a rectangular pulse rate. Now what is the pulse width? T. T is equal to T naught by 3. It's T minus it's the duration from minus T naught by 6 to plus T naught by 6. So the width of the pulse is T naught by 3. So what is the duty cycle? Duty cycle is equal to T upon T naught, which is simply equal to 1 by 3. Now what can you say about the Fourier transform of a simple rectangular pulse with a pulse width equal to t? Right, this is pt. Now what can you say about pf? Pf will be a sinc function with null points at 1 upon t. I hope you know how to find out the Fourier transform of a rectangular pulse. Now if this rectangular pulse is made periodic in time domain, then what will happen in frequency domain? In frequency domain, the signal will be sampled, right? And the sampling rate will be equal to 1 upon T naught. Okay. So it's being sampled. Okay. Let me draw a bigger figure. So this is PF. Now this is PF for a single rectangular pulse for the energy signal, and when it's made periodic, this will be 1 upon T, and when it's made periodic in time domain, in frequency domain, it will become sampled in frequency domain. Okay, and the samples will be available, at a frequency separation of 1 upon T naught, which you can call as the fundamental frequency component F naught. Now this will be 1 upon T naught, this will be 2 upon T naught, and this will be 3 upon T naught, and so on. Now since T upon T naught is equal to 1 by 3, so 3 upon T naught is simply equal to 1 by T, or we can say that the frequency components present in PF, the frequency components present in PF will be 1 upon T naught, 2 upon T naught, then directly 4 upon T naught, 5 upon T naught, then you won't get 6 upon T naught, then it will be 7, 8, and so on. So all the frequency components which are integer multiples of 3, 3 upon T naught, all the frequency components which are integer multiples of 3 upon T naught or simply 3 F naught will be absent in PF. So what are the frequency components present in PF? So the frequency components present in PF are, now it will contain 1 kilohertz, 2 kilohertz, then 4 kilohertz, then 5 kilohertz, then 7 kilohertz, and so on. So these are the frequency components present in this PF. Now what will happen when this xt is sampled using the signal pt? Now what does the sampling do? If a signal is sampled in time domain, then it becomes periodic in frequency domain. Now let us suppose that this is our xf. So it will be having only two frequency components, 0.4 and 0.7. Okay, basically this one is having a higher amplitude. Okay, it's 2 and it's 1. The amplitude is 2 here and the amplitude is 1 here. So 0.4 will be having a higher amplitude. Now let us draw the spectrum of the sampled signal only for the, let us suppose that st is the sampled signal. Then what will be SF? We are drawing it only for the positive frequencies. For negative frequencies, it will be exact replica of what we are obtaining here. Now, one thing more, we will be also having one DC component. So this zero frequency component will be also present in this PA. Now, let us mark the frequencies first. This is 1 kilohertz, this is 2 kilohertz, then 3 kilohertz, then 4 kilohertz, and so on. So we have been asked to find out the frequency components between 2.5 kilohertz and 3.5 kilohertz. So we don't need to go beyond this 4 kilohertz. Now, what will be the frequency components present in this asset? Obviously, one will be at 0.4, then 0.7. Okay, this will be larger. Then the next frequency components, there will be around this 1 kilohertz. So 1.4 kilohertz and 1.7 kilohertz. Also 1 minus 0.4 is 0.6 will occur at 0.6 kilohertz, and then 0.3, 1 minus 0.7 is 0.3. Then 2.4 and 2.7. Again 1.6. 1.6 is obtained by subtracting 0.4. This 0.4 from 2, and by subtracting 0.7 from 2, we will get 1.3. Then 3.4, 3.7, 2.6 and 2.3. No, we are not going to get these frequency components. Do you know why? Because the third harmonic is not present here. So we are not going to get frequency components 2.3, 2.6, 3.4 and 3.7, and this is the major mistake which is committed by most of the students. So we are not going to get these frequency components. Why? Because 3 kilohertz is not present in the sampling signal. Now, so what will be the next frequency component? Again 4.4, 4.7, then 4 minus, so 3.6 and 3.3. So these are the frequency components present in the signal. So we have been asked to find out the frequency components which lie between 3.5 and 2.5. So the frequency components present between 3.5 at 2.5 and 3.5 kilohertz are only two. One is at 2.7 kilohertz, other one is at 3.3 kilohertz. So 2.7 kilohertz and 3.3 kilohertz. So option D is correct. Now moving to the next question. A sinusoidal signal. So this is our sinusoidal signal with the peak values at minus m max and plus m max. It is given that twice of m max, peak to peak value, this is equal to 1.536 volts, right? And quantized into 128 levels. This means that L, number of quantization levels, this is equal to 128. Using a mid-rise uniform quantizer. Now this information is redundant. Why? Because we need to calculate the quantization noise power, and if we are calculating quantization noise power, we are simply supposed to know the step size. It doesn't matter whether it's a mid-rise or mid-rate quantizer. The important thing is that it is uniform quantizer. So the step size will be equal for all the representation levels. So what will be delta? Delta is simply equal to twice of m max divided by total number of representation levels. So this is simply equal to 1.536 divided by 128. So this will be equal to delta, and this will be in volts. So what is 1.536 divided by 1.536 divided by 128? It is 0.012. So this is equal to 0.012 volts. Right. Now, what will be the quantization noise power? The quantization noise power is EQ square, and this is simply equal to delta square by 12. So this will be equal to 0.012 square divided by 12 volt square. Right. Now, so this is equal to, we don't need a calculator for solving this. This we can write it like this: 12 square into 10 raised to power minus 6 upon 12 volt square. So 112 will get cancelled out. So this is simply equal to 12 into 10 raised to power minus 6 volt square. So option C is correct. Now coming to the next question. A 1 kilohertz sinusoidal signal is ideally sampled at 1500 samples per second. Now what is W? W is 1 kilohertz. What is the sampling rate? This is equal to 1500 samples per second, or 1500 hertz. This is equal to 1.5 kilohertz. Now Fs is less than 2W, which means that this is the case of undersampling. Now you must remember one thing, that in GATE examinations many questions have been asked, or many questions are asked, where the signal is undersampled. So you must be a bit cautious regarding it. So it is passed through an ideal low pass filter with cutoff frequency of 800 Hz. Now what is the cutoff frequency of low pass filter? FC. FC is equal to 0.8 kilohertz. So this is cutoff frequency of low pass filter. Now what will be the output signal? The output signal has the frequency. Now there is a signal, let us call it, the signal is empty, and its bandwidth is 1 kilohertz. It has only, in fact, in a sinusoidal signal, it has only one frequency component, which is 1 kilohertz. Now it has been passed through a sampler such that if Fc is equal to the cutoff, the Fs, the sampling rate is equal to 1.5 kilohertz, and then it has been passed through a low pass filter such that the cutoff frequency is 0.8. It's an ideal low pass filter. Now you have been asked the frequency of the output signal. Now it's simple. If we can obtain the frequency components present here at the output of the sampler, then it will be very easy for us to know the output frequencies present at the output of the low pass filter. So what are the frequencies present here? Now I am drawing the spectrum only for the positive frequencies. So the sampling rate is 1.5 kilohertz. So this is, let's call it 1.5. Then the next component will appear at 3, then at 4.5, and so on. Now this 1 kilohertz centered around the origin, this will be always present, and obviously one spike will be also present at -1 kilohertz. Then these two spikes will be centered around 1.5. So another spike will be there, another impulse function that will be there at 2.5 kilohertz, and the third one will be at 0.5 kilohertz. Then at 3.5 kilohertz and 2 kilohertz, and so on. Now, the filter applied has a cutoff frequency of 800 Hz, or its FC is 0.8 kilohertz. Now, if 0.5 is present here, then another 0.5 minus 0.5 will be also present here. Now, what is the frequency component which will be available at the output? Now, this low pass filter will suppress all these frequency components, so they won't be available at the output. The only frequency component which is available at the output is 0.5 kilohertz. So, at the output, the signal will be having only a single frequency component, and that will be 0.5 kilohertz or 500 Hz. So, you can see from here, there is a sinusoidal signal at the input with a frequency of 1 kilohertz, but it has been undersampled. Now, at the output of low pass filter, you are having another sinusoidal signal. Now, since there is only one frequency component at the output, we can say that the signal is also sinusoidal, but this time the frequency has changed from 1 kilohertz to 500 Hz. So, the correct answer will be C. Now, coming to the next question. A rectangular pulse train ST, as shown in the figure, is convolved with signal cos square 4 pi cos square 4 pi into 10 to the power 3t. So, let us write it like this. Let us suppose that the signal is xt, and xt is equal to cos square 2 pi into 2 into 10 to the power 3t. So, this is simply equal to 1 by 2 plus 1 by 2 cosine 2 pi into 4 into 10 to the power 3t. So, I have used the formula cos square theta is equal to 1 plus cos 2 theta divided by 2. So, what are the frequency components present in XF? The frequency components are the DC component, now this corresponds to the DC component, and other frequency component is 4 kilohertz. So, these are the frequency components present here. Right. Now, a rectangular pulse train, as shown in the figure, is convolved with the signal this. The convolved signal will be a. I think there is something missing in this question. Anyway, let's see. Now, what is the time period T0? T0 is equal to 0.1 millisecond. So, what will be F0? F0 will be equal to 10 kilohertz. Okay, that's fine. We don't need any other information. Now the question is, now the signal is not getting sampled using this signal. I was just looking for the time for the duty cycle. The duty cycle is not required over there. Now the signal has not been sampled with this ST. Rather, the signal is convolved with this with this ST. So let us assume that yt is equal to xt convolution with our st, which is given over there. So this implies what will be yf? Yf is simply equal to xf into sf. Convolution in time domain simply means multiplication in frequency domain. So let's plot xf and sf. Now this will be our XF. It will be having only two frequency components, one at DC and another one at 4 kilohertz. Okay, so one is at DC, other one is at 4 kilohertz. I will show minus 4 kilohertz also. So considering negative frequencies, there are always three components. One is minus 4 kilohertz, 0 and 4 kilohertz. Now what can you say about SF? Now this is a rectangular pulse train with a time period of, we don't know anything about the duty cycle. So one thing is for sure, that the frequency components present in the signal, now there will be one DC component, the other component will be at 10 kilohertz, the third component will be at 20 kilohertz, then 30, then 40, then 50, and in between any there is always a possibility that some of the frequency components may be absent, simply because of that will depend upon the duty cycle of the rectangular pulse train. So let us assume that 10 and 20 are present here. Now if we will multiply this XF with SF, now if we are applying the multiplication operation, then what will be the frequency component present in YA? Now this 0 component, the DC component, will get multiplied with the DC component of XT will get multiplied with the DC component of ST. So we will be having one DC component at for YT. Now this 4 kilohertz component, the value for SF at 4 kilohertz is 0. So this will multiply with 0 to give you 0. This will multiply with 0 over here to give you 0. So there will be only one frequency component present in YT, and that frequency component is simply the 0 hertz frequency component, or we can say that we will be having simply a DC component. Now this is a very good question. This says that a random variable x with uniform density in the interval 0 to 1 is quantized as follows. So this is our x and this is our x cube. Now this x is varying between 0 to 1, and now SQ is having two values only. One is 0, other one is 0.7. Now if values of x lies between 0 and 0.3, so they are mapped to xq is equal to 0, and if the values lie between 0.3 and 1, then they are mapped to xq is equal to 0.7. Now the root mean square value of the quantization noise is. Now you cannot directly apply the formula that is root mean square. So you have been asked the root mean square. Okay. So root mean square is simply a square root of EQ square. So first we will find out EQ square, and then we will simply apply the square root over it. Now you cannot apply the formula quantization noise power is equal to delta square upon 12. Why? Because the quantization is not uniform. For 0 to 0.3, it has been mapped to 0, and from 0.3 to 0.1, the signal has been mapped to 0.7. Now it is given that the random variable x has an uniform density. So you can say that the PDF for this x is uniformly distributed between 0 and 1. So this is the PDF between x for the x. So its height will be 1, So there is one demarcation line at 0.3. So between 0 and 0.3 it has been mapped to 0, and between 0.3 and 1 it has been mapped to 0.7. Now how will you find out the quantization noise? Now what is xq? Xq is simply a function of x, right? And what is q? Q is another function of x, right? Q is another function of x. So this q, this is also, let us write it as f. So this will be equal to gx, right? So what will be eq square? Now this is simply equal to minus infinity to infinity q square f q q dq. From here we can write it like this. This is small q, this is equal to small x minus x cube, right? So we can write it like this. This is equal to x minus x cube for limits from minus infinity to infinity whole square, and we can replace this by fxx dx. So this implies what will be eq square? Now for x lying between 0 and 0.3, so we can write it like this. From 0 to 0.3, now it has been mapped to 0, so it will be xq is 0. So x minus 0 whole square, and what is fxx? This is equal to 1, or from 0 to 0.3 this is equal to 1. So it will be into 1 dx plus, and again from 0.3 to 1 xq is 0.7 square into 1 dx. So this will be equal to, simply integrate it, you will get x cube by 3 from 0 to 1 plus x minus 0.7 whole cube divided by 3 from 0.3 to 1. Now what next? Simply simplify it. So eq square will be equal to, it will be 1 by 3 plus, now put 1 over here, so 1 minus 0.7 is 0.3 whole cube by 3 minus, put 0.3 over here, so it will be 0.3 minus 0.7, so it will be 0.4, so minus 0.4 in fact, so it will be minus 0.4 whole cube, so minus and minus will become plus 0.4 cube by 3. So just simplify it, you will get 1 by 3, 1 plus, now what is 0.3 cube? Simply calculate it. It should be 0.3 into 0.3 is 0.09 into 0.3 is 0.027, and 0.4 into 0.4 is 0.16 into 0.4 is 0.064. So this is equal to 1 plus 0.027 plus 0.064. One 1.091 divided by 3, so that will be equal to 0.36, sorry, 36367. Okay, so what will be square root of eq square? So this will be square root of 0.36367. So this will be equal to 0.0 60. It's coming out to be equal to 0.60. I think I have committed some calculation mistake. You can check it out. So from where have I committed, where have you committed the calculation mistake there? The expressions are correct. So we have committed one calculation mistake over here. Okay, it should be 0.3 and not 1. The limits are from 0. So it should be 0.3 cube. So it should be 0.027. So 0.027 plus 0.027 plus 0.064. 0.118 divided by 3. So it's equal to 0.03 0.0393.